Okay. Now that we know what conditional probability is, it makes sense now to move on to a more in-depth and formal handling of the concept of independence. As we already saw in our definition before, that there's a relationship between conditional probability and independence, which is intuitive given the terminology. And once we formalize independence, we really have some powerful tools at our disposal. So let's recall the definition. And here I'm talking about definition of events, or independence of events. So foreshadowing a bit, later on, we'll talk about independence of random variables. We have to define what a random variable is first, of course, but independence of a random variable is not exactly the same as an independence of an event, although they are very closely related, as we'll see. Common definition is that so usual setup, P is a probability measure on omega, then A and B are independent. And the way that I'll often write this, and you'll see it elsewhere, is using this. That's symbol to say A is independent of B, as a shorthand. If and only if probability of A intersect B equals probability of A times probability of B. Okay. Now, what's the more intuitive explanation or definition that we've discussed previously is A is independent of B if probability of A equals probability of A given B equals probability of A given B complement. What is that? Why is that to me, a more intuitive definition is, how do we think about conditional independence? Or how do we think about independence? Well, how do we think of conditional probability? It's how we update our opinions based on information. How do we update our opinion about A given information about B? And here in this intuitive explanation, probably the conditional probability of A given B equals probability of A given B complement is to say, I update my information exactly the same in both cases. And in fact, we can actually prove that if you do that, you actually don't update your information at all, which is to say, if you tell me something about B, it doesn't affect my opinion about A whatsoever. So that is a very reasonable way to approach or to formalize the concept of independence. Okay, so let's think about how we might think about this as a tree diagram. So we can say, all right, we're gonna think about, okay, first, just for consistency, let me actually write this as B given A complement, and B. Doesn't change anything. I'm just switching around the A's and the B's because that's how it's going to look here. Okay. So one way to think about conditional probability, or one way to compute with conditional probability when you're having difficulty kind of conceptualizing, is to draw a tree diagram. So you're saying, okay, first A and then B. I want to think about conditional probabilities of B given A. We're not. So the first thing is either A occurs or A doesn't occur, right? And let's express those probabilities as P sub A and Q sub A. Q sub A is 1 minus A. P sub A is just the probability of A. And then let's express this as well, now after A occurs, we either get B or we get B complement. And after A complement occurs, we're either going to get B or we're going to get B complement. Okay. And so one way to think about this is suppose that, so this probability P, this probability here should actually be the probability of B given A. Let's write that as P. And this is the probability of B given A complement. Let's assume that's also P. Okay, so we're setting some notation down here. Probability of it, PA is probability of A. QA is the probability of A complement, which is 1 minus A. 1 minus probability of A. And P, we've assumed by independence, is the probability of B given A complement is the probability of B given A. Then what can we say by the law of total probability? By the law of total probability, we can express the probability of B as probability of A times the probability of B given A plus probability of A complement times the probability of B given A complement. Okay. And we've assumed that these conditional probabilities are both the same. We've assumed they're both P. All right, let's do it this way. So this is P. This is P sub A. This is Q sub A, which is 1 minus P sub A. And this is P by assumption. So if we factor this out, we can pull the P out. We're left with P sub A plus 1 minus P sub A, which is just 1. And this is P, which by definition was probably a B by assumption was probably a B given A or probably a B given A complement. So that's a proof using the law of total probability that when this is true, when the conditional probability of B given A is equal to conditional probability of B given A complement, then those conditional probabilities have to be equal to just the probability of B. Okay, and we could further, well, using that, we could actually derive this product rule up here by the multiplication rule, because we know that the probability of A given B, right? Or we know that the multiplication rule says that the probability of A and B is, we have to chain the conditional probabilities together. Probability of B given A times the probability of A. But when B is independent of A, we just said that probability of B given A equals probability of B, and we get the multiplication rule back. So the traditional definition, they're interdefinable, so not one isn't better than the other, but you can choose to, you can kind of choose your definition because both cases are true. So both independence if and only if this, or independence if and only if this, they're equivalent. Okay, and we more or less just proved that they're equivalent, but you could button up that proof if you wanted to, and it would be a good exercise for you. Okay, so quick example, just to get our bearings. Assume we have two dice, one white, one black. Okay. We're going to let A be the event. W is the white. Okay, we're going to define W. Yeah, W is the value on the of the white die. B, value of the black die. And we define A to be the event that the two dice add up to 6. We can express this event explicitly if we want. And let's call it an event C, because B is already in use. The event that W, the white die, is equal to 4. Which we write the first die to be the white die. Then it's 4, 1 up to 4, 6. Okay. So then what can we say? Well, what's the probability of C given A? How do we calculate this? It's the probability that both A and C occur. Okay. Well, how many ways are there for both A and C to occur? Well, there's only one. There's one. It has to be a 4, 2. Okay. Probability of A given C is a 1 in 36 chance, divided by probability of A. And there are 5. We already know that the probability of rolling a 6 is 5/36. So this conditional probability is 1/5. What's probability of C? Probability of the white die being a 4. Well, we know there's 6 possibilities. Divided by 36 is 1/6. This is not equal to probability of C given A, and therefore A is not independent of C. So A is not independent of C. You might want to think about why that would be. But as you can see, the probability of C given A is bigger than the probability of C in general. There's, you can have some intuition for it, but it is just a calculation. Okay, let's make some observations so far. Okay. So important, first is a very important observation is that we've observed two concepts, right? Well, no, I'm sorry. First is that A, for every event A, every event is independent of the empty set, and every event is independent of the whole sample space. We can easily calculate this. We can easily show this using the definition, but intuitively we should think about why that is. Why would A be independent of the sample space? Well, think about the sample space is the set of all possible outcomes. So to say that something's independent is to say that if you tell me something happens, it doesn't change my opinion. If you tell me something doesn't happen, it doesn't change my opinion. Well, in the case of saying one of the possible outcomes happened, you haven't changed my mind because you haven't said anything because I knew that already. I already had that opinion that omega, the sample space, was the set of all possible outcomes. So if you tell me that something happened, one of these possibilities happened without any indication of what it is, that's not informative to me. It doesn't help me. Similarly, if you tell me that nothing happened, or actually more easily, if you tell me that nothing did not happen, well, the complement of nothing is the sample space, and we know that we're back in the case that we were, and so I'm not going to change my opinion on that. And so I have, again, independence. Okay. Let's see some other consequences. If A is independent of B, then A is independent of B complement. So we can show this in a number of ways. I mean, it's pretty obvious from this second definition, this intuitive definition, that the definition is symmetric with respect to complementation, right? And so we actually get 3 for the price of 1, or 4 for the price of 1, whatever the case may be, is that all of these statements imply the other. Why is that? The one that we have to prove, well, probability of A intersect B complement, right? We're talking about independence. Okay, let's assume that, so at first we only know that A is independent of B. So we only know that probability of A intersect B is the product probability of A times probability of B. We don't know that A is independent of B complement. We will prove that in a second, but we can't assume it to be true. So you have to be a little clever here. What is A intersect B complement? Remember how we defined A intersect B complement. Come on. So if I have A and I have B, A intersect B complement right here. Another way to think about that, right, was A minus A intersect B, right? So it's the difference. Remember the rule of differences? So this is equal to the probability of A minus A intersect B. Why is that significant? Because A intersect B is a subset of A. So by the rule of differences, this is probability of A minus probability of A intersect B. But now we can use independence of A and B. This is equal to probability of A minus the product, probability of A times probability of B. Factor out the probability of A. What we're left with is probability of A times 1 minus probability of B. What's 1 minus the probability of B? That's probability of B complement. So it's probability of A times probability of B complement. And we're done. We could do the same thing for the others. A complement's independent of B. A complement's independent of B complement. One final observation of extreme importance is independence. So we have two concepts that we've talked about. Mutually exclusive and independent. A and B are mutually exclusive if their intersection is the empty set, if they don't overlap. A and B are independent if there's a few equivalent possibilities. We'll write them, but we'll write them here. Either of these holds, and they're both equivalent, essentially. These are not the same. They do not imply each other, and they're not even really in the same universe in some sense. Why? Why do I say that? This is a property. So mutually exclusive is a property only of the events. So mutual A and B are mutually exclusive just depends on the sets A and B. It says nothing about probability at all. A and B are independent also depends on the underlying probability measure P. So two events A and B, if they're mutually exclusive, they're always mutually exclusive. Doesn't matter what the probability is, has nothing to do with probability. If they're not mutually exclusive, they're never mutually exclusive. Two events A and B might be independent under one probability measure, not independent under another probability measure. So it's totally a probabilistic property. So this is a set theoretic property. Mutually exclusive is a set theoretic property. Independence is a probability property. Okay, so they're different. And you might want to think about under what circumstances can mutually independent events be mutually exclusive events be independent? Almost never. There's one kind of degenerate case, right? If two events are mutually exclusive and they both have positive probability, then if you tell me that one of them happened, you're telling me that the other one did not happen, which you're definitely telling me to update my opinion, right? About the other one. So it affects my opinion, and therefore, most certainly, they are not independent unless one of the two has probability 0 or one of them is empty or situations like that. Okay. So don't make that mistake. It's a common one to think that they're similar and they're not even close. So try not to make that mistake. Okay, that's our definition of probability of independence. We've talked about independence of two events, but a lot of times we're dealing with many different events, arbitrarily many events. So we want to get a more general concept of independence, and we'll talk about that next.